Traditional energy use methods for reducing fuel waste and making every unit of heat count. If you study how pre-industrial societies survived long winters, cooked daily meals, and ran workshops without cheap fuel, one lesson becomes obvious very quickly. Waste was not an option. Wood, charcoal, dung, and oil were gathered by hand, processed slowly, and guarded carefully. What looks primitive at first glance is actually the result of centuries of refinement aimed at squeezing the maximum amount of usable energy from limited resources. These methods are not theoretical curiosities. They are practical systems that still work today, especially for anyone interested in resilience, off-grid living, or understanding how people solved energy problems long before modern infrastructure. Layered combustion was used to control burn rate and heat release. One of the most widespread traditional techniques for reducing fuel waste was layered combustion. Instead of igniting all fuel at once, people learned to stack fuel in deliberate arrangements that controlled airflow and burn speed. In medieval hearths and rural kitchens, dense hardwood logs were placed below, with lighter kindling and brush above, forcing the fire to burn downward rather than upward. This slowed combustion and kept heat steady for hours. You can apply this directly today by loading a wood stove or fire pit so that air feeds the fire gradually rather than aggressively. A slow, controlled burn produces usable heat longer and reduces the need for constant refueling. This same principle is why charcoal kilns were designed to limit oxygen, converting wood into a fuel that burns hotter and longer with less mass. Thermal mass was used to store heat instead of letting it escape. Traditional builders understood that heat wasted into open air was lost labor. Roman hypocausts, Chinese kang beds, and European masonry stoves all relied on thermal mass to capture heat and release it slowly. Thick stone, brick, or clay absorbed energy during peak firing and radiated it for hours after the flames died down. In practical terms, this meant fewer firings per day and dramatically reduced fuel consumption. A masonry stove heated once in the morning could warm a home well into the night. Modern users can replicate this by incorporating stone, brick, or earthen materials around heat sources. Even placing a dense surface near a heat source in a small space increases efficiency by storing otherwise wasted heat. Indirect cooking methods prevented constant fuel replenishment. Open flames waste fuel when food is cooked directly over high heat for long periods. Traditional kitchens avoided this by using indirect cooking zones. Cast iron pots were pushed to the edge of embers, bread was baked using retained oven heat after the fire was removed, and stews were simmered slowly rather than boiled aggressively. A historical example is the hay box cooker, widely used in the 19th century. Food was brought to a brief boil sealed in an insulated container and allowed to finish cooking using retained heat. This method could reduce fuel use by more than half. Today, this can be replicated with insulated containers, thermal cookers, or even improvised setups using thick cloth and enclosed boxes. Fuel preparation was as important as fuel choice. Traditional societies invested enormous effort in preparing fuel properly. Wood was seasoned for years to reduce moisture, dung was dried into cakes, and charcoal was carefully graded by size. Wet or poorly prepared fuel wastes energy by burning off moisture instead of producing heat. For modern application, properly seasoning firewood alone can reduce fuel consumption significantly. Dry wood burns hotter, cleaner, and faster, meaning fewer logs are required to achieve the same result. Airflow control was the hidden technology behind efficient fires. Ancient stoves and hearths were rarely open holes in the ground. They were engineered systems designed to regulate airflow. Narrow flues, adjustable vents, and elevated fire beds allowed precise control over oxygen supply. Less oxygen meant slower combustion and longer heat output. This principle is directly usable today. Adjusting air intake on modern stoves, sealing gaps in fire chambers, and using lids on cooking vessels all mirror historical practice. Every reduction in uncontrolled airflow translates into fuel savings. Waste heat was captured and reused whenever possible. Traditional households reused heat instead of letting it dissipate. Cooking areas were built adjacent to sleeping platforms, ovens were integrated into walls, and chimneys were routed through living spaces to warm rooms before venting outside. A modern equivalent might involve placing water containers near heat sources to preheat water passively, or designing living spaces so that heat from cooking areas benefits the rest of the structure. Fuel choice was matched to task, not convenience. Pre-industrial users understood that different fuels had different purposes. Fast-burning fuels were used for quick tasks, while dense fuels were reserved for long heating cycles. Using high-energy fuel for small jobs was considered wasteful. This approach remains relevant. Using charcoal for long simmering, wood for space heating, and quick ignition materials only when necessary reduces overall consumption. Matching fuel to task is one of the simplest yet most overlooked efficiency practices. These methods still work because they were shaped by necessity. Traditional energy systems were refined by generations who could not afford inefficiency. Every technique discussed here emerged from lived experience, not theory. When applied today, these methods reduce fuel use, extend burn time, and increase overall energy effectiveness without relying on modern technology. If this kind of practical historical knowledge matters to you, subscribe to Wisdom for the Journey. Share this guide with others who care about real, usable history, and keep these hard-earned lessons alive by putting them into practice.